मैसेज है ग्रुप में, इमीडिएटली ज्वाइन करें. Okay, sir. So I think now I should start because it's already 2:30. So if you permit, sir, we can start, sir.
Yeah, please.
Yeah. So good afternoon to all. Welcome once again. Welcome you all in the third lecture of the day. So Professor S.G. Dani sir is with us for today's talk. So without taking much time, I would like to invite to Professor Dani sir for his talk. Sir, please.
Thank you. Welcome all to this third session of the set of lectures. Let me begin by opening my presentation. Suppose you are all able to see it.
Yes, sir. Yes, sir. Visible, sir.
This third session is on the Siddhanta tradition. This tradition which is recognized by the names Aryabhatta, Brahmagupta, Bhaskara, and many others actually. And if you go in that tradition, the this tradition itself is well, Aryabhatta, as you know, is from the 5th century, born in 476. But Siddhanta tradition is characteristically the tradition which developed out of study of mathematical astronomy. So in this study, astronomy had an important place by that time in the daily life in terms of timekeeping. I mean, of course, the interest in the stars, of course, is also something inherent to human interest. But apart from that, it served in terms in timekeeping. So in terms of writing with Panchangas, understanding the year, seasons, and so on, and then extraordinary phenomena like eclipses, etc. So the curiosities which sort of sometimes they were looked upon with fear, with kind of omen, etc., etc. So they had an important place in the daily life, practical life in some sense. The tradition of astronomy and even some element of mathematical astronomy is more ancient than that in India. There is the Lagadas Vedanga Jyotisha is and in that you have some degree of mathematics, especially arithmetic or solving certain kind of equations, etc., is important. However, I'm not aware of any geometrical inputs that can be included from there. So, serious geometrical inputs start with the mathematical astronomy at a later stage, and this is greatly influenced by the Greek mathematical astronomy. So, there was, I'll not go into the details of the Greek tradition. So, early centuries of the first millennium saw a rise of interest, especially after the advent of Alexander the Great. And so, there's some infusion of the Greek mathematical astronomy. So, for instance, some of the things, basic units of measure like degree and so on, they are Greek inputs. There's more to it, and it's not my plan to go into that here. But there's just just to ask you to keep in mind this background. So this generated a tradition which lasted over 1,000 years. So we are starting this thinking of roughly from the period of Aryabhata. I'll say a little more about this point uh, as we go along, and then it lasted well, at least until Bhaskaracharya, and until at one time there was thinking that that was the sort of pinnacle and everything is sort of at a plateau, but it turns out that the tradition lasted even beyond. There's names like Narayana Pandit, who comes from the later period. So about 1,000 years the tradition continued in a certain definite form, and then it was also responsible for played an important role in the rise of the what is known as the Kerala School of Mathematics, which is something we will not be going into because by then it's not the basic geometry that needed any further inputs, but it went into infinite series and various other things which are akin to calculus in some way. I mean, many ideas of calculus are sort of inbuilt in the Kerala mathematics. So, uh, among other things, this period also saw a rise of trigonometry and Hamilton equations, which again is not going to be part of my talk here. We are going to focus on geometry. Okay, so the major contributors from the tradition are Aryabhata, and the very celebrated work is Aryabhatiya, which is kind of the foundational work for the tradition in some sense. Everybody would sort of base themselves on that. Not always directly. Brahmagupta wanted to contradict many things, but there was always the Aryabhatiya was also always in some way the reference point for whatever people usually say. Then there's Varahamira. Varahamira's contribution is mostly to astronomy, so it will not have much to do with his work. Then there's Brahmagupta, the name which you must have heard frequently. Bhaskara the first. This name also came up in various contexts. Bhaskara the first was a contemporary of Brahmagupta, and he composed the Mahabhaskariya, a commentary on Aryabhatiya, uh, and another work called Laghu Bhaskariya. Bhaskara the second, or Bhaskaracharya, of course, is a familiar name to all, even in this workshop. So, and he composed the Siddhanta Shiromani. Siddhanta Shiromani, it has these four parts: Lilavati, Bijaganita, Ganitadhyaya, and Goladhyaya. So, and then I mentioned Narayana Pandit. Narayana Pandit again has to. Okay, we will has some contributions to geometry. Maybe I'll mention quickly at the end. But, so these are some of the major names that we'll be talking about. Now let's sort of start at the beginning, so to speak. Again, every time any serious discussion of geometry starts with the circle. The straight lines are somehow simple, and it's no surprise by that by then people know new things. All that is needed to know about, say, straight line figures like rectangles, trapezium, etc. Though it's we are going to say more about that, but I think because the general quadrilateral is something more general. We will come to that later. But whatever reason, we're going to start with the value of pi. And about pi, we have had a look into what people thought about it earlier. In the Shulva Sutras, you don't really find any definitive idea of a ratio to be kept in mind and applied in very different contexts, etc. There usually the issues which involved the ratio were dealt with in ad hoc fashion each time, depending on the problem. Now, in the Jaina context, I mentioned that they had a definite constant square root of 10, which had some error, but nevertheless, as far as they were concerned, it was sort of served the purpose. Now, interest in more accurate values of pi seems to have come up not only in India but across the world. I mean, among the Greeks and among the Chinese and so on during the early centuries of the Common Era. The and Ptolemy from the second century, for instance, had very similar approximation for pi. Similarly, Liu Hui in China also had accurate value for pi. In the Indian tradition, the Aryabhata describes a value for pi in the Aryabhatiya, and here is the verse: Chaturadhikam Shatamashtagunam द्वाषष्टिस्तथा सहस्राणां अयुतद्वय विष्कम्भस्य आसन्नो वृत्तपरिणामः. Chaturadhikam is 4 more. So 100 more, 4 more than 100. Anyway, it will follow according to what you see translated here. Multiplied by 8 and add to that 62,000. And this is the nearly approximate measure of the circumference of a circle whose diameter is 20,000. So at that time, they did not have these our decimal point notation with decimal fractions, etc. So general tendency was to have do calculations, do formulate things which would involve only integers in their expression. It seems to be a motivation for choosing this 20,000 seems to be something like that. So that the whatever remainder in the fraction that you might need in the calculation, that should be possible to ignore. So so diameter being 20,000, radius will be 10,000, and then from that there's actually no definitive way of saying how this was calculated, but generally I think it is believed that it is by approximating the circle by regular polygon of a high number of sides, and in this case it appears that the Aryabhata would have used inscribed regular polygon with 384 sides. So that is the 6 times 2 raised to 6. So you start with a hexagon. Now you know the perimeter of the hexagon, because it consists of 6 equilateral triangles with radius as one of the sides. So therefore, if the radius is 1 unit, then it will be 6 times that. From that, using the Pythagoras theorem, you can calculate the perimeter of a 12-sided regular polygon. From that, you can calculate the perimeter of 24-sided polygon. Each time you can double, so that in 6 terms you get, in principle, you can calculate the perimeter of a 384-sided regular polygon, and that's the value that seems to have been taken. But this is just in principle. But if you actually want, when you try to do these calculations, and if you are going to ignore fractions, etc., then you need to be a lot more careful in doing managing your calculations. You have to minimize the number of times you will have to take square root and ignore, and keep track of that, etc. And only with efficient way of doing that, you can get the answer. Yeah, otherwise, the errors will keep dominating, and suddenly it will shoot out. If you can, I mean, I've tried it myself, and I urge you to look at it, try it yourself. And uh, the same value is stated. I mean, is later mentioned by Bhaskaracharya, and Ganesh Daivadnya, who is a commentator on Bhaskaracharya, mentions that this figure that it was calculated by using a regular polygon of 384 sides. Actually, however, I found that the argument of Ganesh Daivadnya is quite unsatisfactory in that respect. What he actually does hardly justifies the way in which one would have concluded that. But this is only a side remark. There is, nevertheless, it is it's true that about 300 this regular polygon of 384 sides does fairly approximate, and that would have been taken as the value. Curiously, actually, the regular inscribed, it being the regular inscribed polygon, the value should have been less than the actual one, but this answer it comes out to be more because of the rounding up. So, which is a part of the game in some sense. Okay. Then, so as you know, we are also sort of been emphasizing on the Pythagoras theorem, that it was known in the Shivasitra, that was is part of the Jaina tradition, etc. And it's worth recalling that it's also mentioned in the Pythagoras theorem. Here is the verse for that, but let me not spend time in reading. Maybe I'll have more things to do. So, uh, yeah. So now the first line states the Pythagoras theorem. Vishcheva bhuja koti vargascha karna vargaha saha. So that it is koti varga, karna varga together give the bhuja. Bhuja is the hypotenuse. Varga. The second part of the verse states, with reference to this figure, that AE times EB equals C square. So this is something similar to this we actually saw in the Jaina calculations. And here you see this is immediately this assertion is succeeds immediately the Pythagoras theorem. So the tradition clearly shows that this was observed as a consequence, as one of the consequences of Pythagoras theorem. Though, of course, one cannot always infer this. Sometimes one does find a mix-up of things which are not related, but I mean, nevertheless, the immediate fact of the being put together does suggest, in this instance, that that was meant as a consequence, and it does follow as a consequence, of course. Okay, so here is another verse which yeah. So I'll leave aside the Sanskrit part. The verse describes, with reference to this figure, the okay, here the bit of geometry to be described here. So what is the context or framework? There are two circles, intersecting circles, and grasa is being eaten up. So a part that is that is eaten up. So by the other source. So I mean, like this sort of context occurs in the eclipses, where the part of the sun is covered by the Earth or the moon in between, etc. So here this is the formula for this setting. That so this BC. Now, when you have BC, the part of the circle, it is equal to AB times BD, AB times BD divided by AB plus D, A- uh, AB plus D. So, and then similarly, the CD is equal to D times BD plus AB, AB plus D. So in other words, these are first of all AB, BC and DC are proportional in a way, and this gives the precise formula. Now, you can readily see that is something related to astronomy, not just the eclipses. I mean, they would probably have to calculate the uh, look at the orbits also in terms of the circle, because orbits are not exactly circular, but they're modeled as being circular in some way, and probably it could also be useful. My own knowledge of astronomy is somewhat limited, so I can't comment very definitively on that. But this kind of situation could occur with regard to orbits, approximate orbits as well. Okay, so I have sort of covered some things from Aryabhatta, typically the basic geometry, and then something extra that we have noted in terms of the astronomy related phenomena. Now, let me move on to Brahmagupta. So, uh, this was Stula Phalam Sri Chaturabhuja Bahu Pratibahu Yogadala Gataha Bhuja Yogartha Chatushtaya Bhujona Gatat Padam Sukshmam. Now, this is the formula for the area of area of quadrilaterals. There are two parts here. The first line states that the gross sthula is gross approximate area of three chaturabhuja, and I'll come to more about three chaturabhuja, what it is. The area of a three chaturabhuja equals the product of the average lengths of the pairs of opposite sides. Bahu pratibahu yoga dala gata. You take the pairs of opposite sides and yoga dala. So you have to take average. You divide by 2, therefore it means you are taking the average of the opposite sides and take their product, and that is the approximate area for is said to be given to be approximate area for three chaturabhuja. Now there has been quite a bit of discussion and confusion to an extent about what three chaturabhuja means. Now, typically in literature, starting all the way from anybody following Brahmagupta, this has been taken to be mostly to mean that Brahmagupta meant it for both triangles and quadrilaterals. Either that the figure in question is either triangle or quadrilateral, or quadrilateral with triangle as a special case, when with one side being taken to be 0. Now, recently there has been an interpretation that which varies from this, and and that is motivated by the second part. So let me first go over the second part and then say more about it. So here yeah. So, okay. So now, the second part is actually describes this formula. Second line gives the formula. Sorry, this second A should be S. So, the square root of S minus A, S minus B, S minus C, S minus D, where S is the semi-perimeter. So, we have a quadrilateral with perimeter AB, 4 sides A, B, C, D. And S is the semi-perimeter, which means you add all the 4 and take half of that, and take this product and take the square root, and that is given as the sukshma or fine area of the Trichaturabhuja. Now, as one knows that this formula would be correct if exact if it is the quadrilateral is cyclic. So cyclic quadrilateral, namely if the vertices lie on the vertices of a quadrilateral lie on a circle, then this works out to be an exact formula with S in place of A here. So uh, yeah. So based on, I suppose, based partly on this observation, the speculation is now, the belief now is that Trichaturabhuja was probably meant as a technical term uh, to convey the cyclic quadrilateral. So Trichaturabhuja is meant, the interpretation is that it was meant to be a technical term for cyclic quadrilateral. Now, there are, of course, some further arguments advanced in support of the hypothesis, in the sense that, for instance, if you were to mean triangles themselves, then why would triangles we could discuss separately later, etc. There are some kind of arguments about the arrangement, etc. And in any case, that after all, if he was saying something, it must have specific reason for it, etc. I mean, well, I won't presume to convey the argument of the authors. This is primarily Kishanasamy who has papers on this, and I don't think I can exactly convey what the argument is. But it's difficult to say whether that can be taken as a final verdict in the status of the matter, because it is, for instance, it's not quite common to suddenly use technical terms without any explanation, etc. So there's sort of matter of doubt there. So that's where things stand as far as I understand, or I can consider to be proved or seen. Okay, so Brahmagupta himself invariably applies the formula or things like this only for the case of cyclic quadrilaterals. So there is no internal contradiction about or inaccuracy in the working. So if it's a completely consistent thing to assume that Trichaturabhuja, by Trichaturabhuja he meant cyclic quadrilaterals. However, then still the point remains, then why did he talk about this approximate formula in the same breath, same sentence, same unit? So first, it's note that this formula is actually approximate formula is actually holds only when it is approximately a rectangle. So it doesn't hold for anything which is not approximately rectangular. Then, so in particular, it doesn't hold for a general cyclic quadrilateral either. So if there is a question of exactitude, etc., that's to be attached, then there is one also has to answer why these come together. So there's more to be explored than and answered. Okay, Brahmagupta himself, as I said, has used the formula only for cyclic quadrilaterals. However, this caveat, if at all it was meant to be a caveat, was lost over a long period. Sridhara and Mahavira recall the formula and do not show any serious awareness of there being something amiss about the formula being not valid. I mean, I'm talking about the second formula, which is supposed to be a fine formula. So, as late as the 14th century, Thakur of Heru has also stated the formula without mentioning the caveat that it is true only for the cyclic quadrilaterals. In the Siddhanta tradition, however, we are talking here, the names above are from the Jaina tradition. In the Siddhanta tradition also, until a long time, it seems to have been sort of taken as it is. In fact, I'm not sure if there are any major expositors during the period, and at least that we know about mini-slate. Bhaskaracharya in the 12th century and Aryabhatta II, little before him, the 10th or 11th century before him, were very critical of the formula. And their argument was that the four sides of a quadrilateral do not determine the area of the quadrilateral uniquely. You can take four sticks, for instance, and you can make alter them, keep shifting, say, making different angles between them, and to produce more different possible areas. So therefore, the with that argument, and then Bhaskaracharya illustrates this in various ways, and comments that one who does not realize this is a fool or a devil, Mukova, Pishachova, or something like that. So it is, I mean, the episode is quite interesting itself, and I have a separate paper on this aspect of Bhaskaracharya's treatment of the work. So, and there are various things that he says about that. And, he first describes the statement, and then gives a counterexample, and then gives different constructions by which one can see it with calves, etc. Okay, so anyway, so we have, as far as cyclic quadrilaterals were concerned, which presumably were the ones that were important for astronomy, which is how Brahmagupta seems to have focused on the study of those. It's an exact formula, and rather remarkable for that. And of course, for the triangle, as a degenerate case, it reduces to the area of a triangle, which you all know we study in school, and that goes by the name of Heron. And so, but for as far as the quadrilaterals are concerned, cyclic quadrilaterals, this formula is original to Brahmagupta. So it's Brahmagupta's formula for areas of cyclic quadrilaterals. So one wishes that there is no such confusion, and it would have been clear, there would have been a clear story of cyclic quadrilaterals. So. Apart from the area, Brahmagupta also describes the diagonals of the quadrilaterals. Yeah, diagonals of applies. This again applies only to cyclic quadrilaterals. Brahmagupta, in fact, it does not involve the non-cyclic quadrilaterals in context as far as I know. So, and so the two diagonals of cyclic quadrilateral are described by this. So if A, B, C, D be the sides of the quadrilateral, the diagonals are given to be AB plus CD times AC plus BD divided by AD plus BC. And the other one is AD plus, there's a bracket missing here. AD plus BC multiplied by, well, it's by symmetry. One has to interchange it. ABC. So AD plus BC, AC plus BD divided by AB plus CD. So yeah, so quadrilaterals and their diagonals they're completely described as far as cyclic quadrilaterals are concerned. And it's known that this in the West, this formula was rediscovered by Snell in 1617, so 17th century. Apart from the formulae, I mean, see, typically construction of figures had to be thought of in terms of integers, because when you wanted to construct something, unless you are just looking at a random figure, you needed to have the measures to be integers to be able to describe. And one of the basic interests was to construct quadrilaterals with rational or specifically, let's say, integer integer sides. So another topic that may be recorded is the construction of quadrilaterals with rational or integer sides. जात्यद्वय कोटिभुजाः परकर्णगुणाः भुजाश्चतुर्विषमे अधिको भूर्मुख हीनो बाहुद्वितयं भुजावन्यौ. So the kotis and bhujas of the two jatya triangles. Jatya is the triangles that you use for producing the basic triangles to starting points. Triangles multiplied by each other's hypotenuse. So you take two triangles with integer sides, let's say, which are easy to produce. You can take and then you take multiply by the hypotenuse of each other. So the hypotenuse of the after you have done this respective multiplication, the hypotenuse will become common, same. So then you take that as length and put the two triangles on the two sides. So then the longest is the base, the least is taken to be the base, the least one the face, the remaining two sides are the blank sides. So jatya are the yeah, sorry, I forgot to say. Okay, the construction works for this construction would work to produce a quadrilateral, but this it should be cyclic precisely when the jatya or the triangles that you start with, they are right angle triangles, and that is as I said, Brahmagupta, that is that's crucial. So you start with, therefore you start with two right angle triangles, then do this the thing about multiplying by the size of the hypotenuse of the other one in each case. So then you get two right angles with a common hypotenuse, and therefore you put when you assemble these two along the common hypotenuse, you will get the quadrilateral, which is cyclic. Now, of course, once you have such a quadrilateral, you can again manipulate, interchange the sides, etc., and a variety of things that it does, which I don't think we will spend time on that. And there are various examples, specific examples also constructed. Okay, now let's come to Bhaskaracharya. Bhaskaracharya's Lilavati devotes a chapter to planar geometry called the Kshetra Vyavahara. So this is one of the later chapters actually. The chapter begins with the statement of the Pythagoras Theorem. After just the one verse introducing the terms involved, and goes on to discuss various examples, exercises involving it. Now, the general method for constructing the integer-sided right-angle triangles, so those corresponding to Pythagorean triples, this is discussed with one side given. So, okay, this is a little general problem. I mean, so one side given. So, you are given one integer side, then how do you produce two other integer sides such that the triangle form makes a right angle triangle? So in the course of that, basically this is one of the basic things that one learns in number theory, for instance, which is covered in Lilavati. For any two positive integers x and y, we get Pythagorean triple. So if you take x square minus y square, if you take any two positive integers x, y, then the triple x square minus y square, 2xy, and 2x square plus y square. So these are all integers, and if you take square of this plus square of this, that will be equal to the square of this. That's because when you, I mean, it's clear that when you square this, the square of this minus square of this, the difference is only the twice with the minus xy coming here with a negative sign, and twice x square y square coming here with the negative sign, which is the difference of those two is 4x square y square, which is the square of this. So such a triple always gives Pythagorean triple, and using pointing this is pointed out, and using this, so given your number, you either adjust it as you write it in this form, and then to get to take these two as the other sides of the triangle. So that's a way of constructing right angle triangles with any desired side. Okay, so now area of quadrilaterals. So here I'm going to repeat some of what I said in this context. So Brahmagupta's formula is stated in the verse. So it's, okay, Sarodor Yutidadam Chatusstitam Bahubhir Virahitam Cha Tadvadhat. So Moolam Asphutaphalam Chaturbhuje Spashtameva Muditam Tribahuke. So here what he's saying is the following. So Sarvador Yutidalam is the S that we're talking about. You take the sum of the four sides and they divide by that. Chatusstitam Bahubhir Virahitam. So you place it at four places and subtract. Virahita is you want to subtract each side from each of them, and tadvadhat, and multiply them. Vada is corresponds to multiplication. So by multiplying the two, you are killing the individual identity. So you take the product of the four. Now, so this is the product that we talked about here with S here, S minus A, S minus B, S minus C, S minus D, square root. Square root is moolam. So here, up to here, we constructed the product. And so moolam, you take the square root. Now he says it is asphutaphalam chaturbhuje. So it is gross area. Well, that's one possible. Asphutaphalam, that's the term. So let's reserve it and understand what it should mean. And then for chaturbhuje and spashtameva. Spashtamevam uditam tribahuke. For triangles, it's supposed to be exact. And now for quadrilaterals, he says it is asphuta, whatever it means, asphutaphalam. So what I have commented here is specifically what sense he meant to convey by the term asphutaphalam is unclear. It has been translated as imprecise. He actually later in Lilavati, he actually goes on to ridicule, as mentioned earlier, ridicule it. He does not realize, however, that the formula is valid for cyclic quadrilaterals. In Lilavati, unfortunately, somehow the concept of cyclic quadrilaterals doesn't seem to appear. And of course, some of the quadrilaterals in the examples, they are quadrilateral, but the idea that they form a special class and have some special properties doesn't figure in that. So, and especially the fact of not seeing that under some conditions it is true anyway, having missed that somehow seems to contribute to his ire. I mean, it seems as though what is this? They are doing some peculiar, strange statements and so on. That's the sense what one gets from the description there. Interestingly, the Kerala school, we work in Mukti Bhasha, the second line of the verse appears in the emended this is n here, emended form, altered form. मूलमत्र नियतश्रुतौ फलं त्रस्य बाहुजमपि स्फुटं भवेत्. So this second line is being amended, modified. I mean, in the Kerala school, they were, apart from Aryabhatta, they were also following up Bhaskaracharya, the writing commentaries on both these. I mean, they were serving as their basis for the developments. And there, this part so is modified to say, instead of asputafalam moolam asputafalam, it is said there moolam atra niyatashruto. So when the diagonals are determined, there is something determined about these. So it's a kind of restriction being imposed, and which is not directly saying circular, but there has to be some way of determining that the four sides somehow determine the area, and when that is determined, the area is given by that. So that's the modification. Of course, in triangles, it becomes correct. So okay. Let's go over to the circle in Lilavati. Bhaskaracharya repeats Aryabhatta's rule, Aryabhatta's value of pi in the form of 3927 divided by 1250. So here it's actually just the factors that are cancelled. So it was the description, the diameter size is taken to be 20,000, which is 8 times this thing. So, and then the 62,000, whatever it describes, is divided by 8 will give you 3927 as this as the fine value. And another interesting thing is the Bhaskaracharya gives 22 by 7 as value for practical purposes. I think in the Indian literature, I think it's the first time that 22 by 7 is taken as a practical value. Until then, the square root of 10 from the Jaina tradition was, of course, very convenient, simple value, which was very common. And the other alternative simple possibility for calculations of 22 by 7 is introduced, I think, for the first time by Bhaskaracharya. Of course, one knows that in the Greek tradition, it goes back to Archimedes, and it was common in the Greek mathematics. It's not clear whether it's somewhat likely that Bhaskaracharya was probably not referring to the Greek value, but there is, I think, those of you who heard Venkateshwar Pai's lecture, they would know that wherever there were complicated denominators, complicated fractions, they would produce simpler variations of that, close to those, by an operation of the mutual division, which would be called continued fraction strategy. So they're not continued fractions as in the sense of identifying number with fraction, etc., but the same algorithm, same procedure for that was used to get approximations, and it is quite likely that 22 by 7 was simply obtained by applying that method to this fraction. So 22 by 7 is the simpler version for the Aryabhatta's value, which is equal to this. I mean, naturally, it works out to be that. Whether that was the way it was calculated is something we would not know, but that seems very plausible, because I don't think there are no other Greek elements appearing in Lilavati. So this would be independent. Now, various relations between chord and the corresponding arrow and the diameter that are deducible from Pythagoras theorem are described in the chapter. Now, the formula that the kind that we discussed in the Jaina case, that similar, and so that appears, for instance. So the interrelations between the chord and the diameter, etc. Apart from that, there's also an approximate formula. There's also an approximate formula given for the length L of a chord in terms of the length A of the corresponding arc. You may recall that we had a similar thing for the some similarity, but here is in the details it's not it's the same. So the arc is being described in terms of the length L of a chord. This is the formula for the chord in terms of the diameter and the arc. Yeah, diameter and the arc. These are the things. And so here, yeah, the L is equal to 4 times the diameter times the arc, and then product C minus A, circumference minus the arc. So the total circumference minus the arc and multiplied by the arc, multiplied by the diameter, and divided by this number. Now, this is given as the approximate formula. So I think I'm sort of hiding something. You recognize that writing a chord is very close to, is similar to taking the sine of an angle. So if you take half the chord of half the angle, then that is the sine, right? So this is related to the Bhaskaracharya's work on trigonometry as well. So it's actually relates to the formula for sine. And this formula, in a way, actually is called as a trigonometric formula for sine. Is something older in the Siddhanta tradition. It goes back to his namesake, the first Bhaskara. First Bhaskara in 628 in his Mahabhaskarya has a formula for sine, well known for the as Bhaskara sine formula. Actually, the formula appears also in Brahmagupta, but it's usually attributed to Bhaskara for reasons that are not quite clear to me. So anyway, so this has been a standard form. So here it is. I am presenting it, and in Lilavati also it comes as a formula, approximate formula for the chord. For length of the chord, but basically this thing is related to trigonometry. So it's a version of of Bhaskara's first Bhaskara's sine formula. So if you make the appropriate substitutions, that is what it exactly corresponds to. Yeah. So now, what about non-planar figures? So okay, so now here there is a single verse which actually tells you the area of a disk, area of a sphere, and the volume of a sphere. So it is all in one. So I don't know why I did not copy that, but anyway. So here it is. Here is the statement. So the area of a disk, area of a disk equals 1/4 of circumference times diameter. This, of course, is the first simple thing that you learn, and that's described here. Lilavati does not have proofs. There's in the Vasana there are proofs for certain things, but I don't think this is explained. But this is something very classical. So maybe it might. I mean, Bhaskaracharya seems to go into details only when he feels that he needs to. In some, and this is not one of the steps. I think I could be wrong. So area of a disk is 1/4 of the circumference times diameter. This is our standard formula. Then surface area of a sphere with the same radius, of course, is 4 times the area of its equilateral disk. The things described, it's to start with a disk, its circumference and diameter. So in terms of that, everything is explained. So area of the surface is now so 4 times the area of its equatorial disk. So for a sphere, you have the equatorial the uh, disk formed by a great circle, for instance, and then take the area of that, the flat area of that, multiply by 4, and that is the area of the disk. So so in our usual formula, it will be 4 times pi r square, which is the area. The volume of the sphere is 1/6 of surface area times the diameter. Now notice that all this avoids any reference to pi. So you have both the two things given. So the circumference, of course, involves pi in its description in terms of the diameter, but given that the circumference and the diameter, so everything else is described in terms of these two, thus making uh, thus making the relations exact. So as there are no notation for pi, if you wrote some approximation like Sridhara did, then the formula would have seemed approximate. Here, I mean, these being simple interrelations, the formula are exact and correct, of course, for the first time in the Indian context, as we said. Earlier, there is no one correct formula for either for volume nor for area of a sphere. So, as I have recalling again that the earlier texts bring in the ratio in their exposition, and in absence of any notation for it, are constrained to resort to approximations, which is avoided here because of the way it is presented. Now, these are some of the topics I have covered. I don't. I mean, in a way, the subject is vast, so I don't think we could have. And it's possible to give a glimpse of the things in. So let me just summarize what other things that one can look for in this context. So with a brief mention of the other geometric topics dealt with in the Siddhanta tradition, and in the aftermath, not covered here. Let me interested. Okay, so volume of irregular ditches, etc. This come, by the way, comes in a different chapter. So there are other chapters on excavations and shadows, etc., which are geometry related. So volume of irregular ditches, piles of grain. So for example, you have you make a pile of grain, then depending on the nature of the grain, the pile will be less or more, and so on. And so first of all, there are formulae for the volume in terms of the height and the diameter. So which is of course like the I mean conical. It's a conical shape, and then it gives the formula. Then depending on the grain, there's also the description in terms of possible heights. So how much it will be, etc. Then there are also geometry related topics such as shadows that will be not gone into. Also, as I said, though at one time it was thought that the Siddhanta tradition saturated with Bhaskaracharya II. That's really not true. There's a good deal of work. I mean, in terms of technical virtuosity of Narayana Pandita, which have not gone into, especially this, more detailed understanding of cyclic quadrilaterals, etc., is covered. I would not have been possible for me to go into that here. Then there's also the later Kerala School of Mathematics, which it's no the geometry part was the basic geometry part was already dealt with in the earlier works, for instance. So the of our from Aryabhatta to Bhaskara, to which they were privy to. Not all of it, but major works of from the Siddhanta tradition were known to them, and they were following it up. In the Kerala tradition, the main contribution was trigonometry and the related kind of calculus method. So and but that involved a good deal of geometric understanding as well. So it's like in the same way as calculus depends on basic geometry to an extent. So the area relates to the area under a curve, for instance, is something one of the crucial things in it. And that is in terms of summation, etc. So these are some of the later developments in that, not exactly in geometry, which in fact was sort of saturated by them, but there are other various things developed. Again, as I said, the various. I already mentioned one emendation of the correct things about cyclic quadrilaterals, etc. So some of that is also possibly covered in Kerala School of Mathematics. So anyway, we will not have. I will not be going into that. So with that, let me thank you for your attention.
So, is there any question from audience? Yes. Any question?
Okay, just one or two remarks.
Yes,
I'm
sir.
sure Professor Dani himself would have dealt with these things.
Sorry?
If he had, I'm saying, Professor Dani himself would have dealt with what I'm going to say if he had more time. But anyway, he was saying that this circumference of a circle, area of a circle being area of a circle in Lilavati.
Yeah.
So you said that doesn't depend upon the value of pi. So that is, of course, correct. What I'm saying is the proof also. The proof. Am I not audible? I don't know.
Yeah, the voice is cracking somehow. Maybe.
Maybe I'll talk slowly. The proof in Buddhi Vilasini also does not depend upon that. He lays out the circle as a series of triangles.
Yeah.
And then sums the areas of that. So then it naturally comes that it is circumference into this thing, diameter by 4. Yeah. It comes that. And regarding this area of the sphere, of course, there, I think in Siddhanta Shiro and Goladhyaya, he gives the proof. There it depends upon the summation of the signs, 24 signs.
Summation of?
The 24 signs.
Okay.
Some summation, the 24 signs it comes. So it doesn't come as naturally as in this thing, but see, he may not get it as the exact formula, but he rightly guesses, that it must be close to it, because when he sums the signs, So finally, of course, he just puts it as, it is very close to, by numerical computation, he finds it is very close to
very close to
the formula you gave. It is a 40 of the equatorial area, and so he says that is the thing. Yeah. And volume, of course, others had already commented. Volume of sphere, it doesn't involve any calculus because only summation of the cones, volumes of cones. Yeah. So it comes like that. But volume of area of sphere and volume of sphere, that is dealt with in Yukti Bhasha, more or less in the usual calculus integration method. Yeah.
The detailed proofs perhaps appeared for the first time in Yukti Bhasha.
Yeah.
I don't know because,
Yeah.
Okay. So, any other question from audience?
someone has raised a hand. It says, I don't know.
Yeah, please. Yeah, Anuradha Pradhanji.
Anirudh, not Anuradha.
Sorry, I'm very sorry. Anirudh Pradhanji, sorry.
It's a joke, it's a joke.
Yeah, please ask your question.
Hello. Pradhan sir. Hello. Pradhan sir, are you here? He has left.
क्या हुआ?
So I think Pradhan sir is not there. So is there any other question from any other participants? Okay, so I think no more questions are there. So let us thanks to our professor for giving wonderful lecture on geometry of ancient mathematics. So thank you so much, sir, for describing many important concepts from ancient mathematics: Pythagoras theorem, intersection of circles, diagonals, and then Brahmagupta's area formula, and many other things. So lecture was really very wonderful and enjoyed by the participants. And thank you so much, sir, for delivering wonderful lecture. Thank you so much. Thank you. So we will meet again. So we will meet again after, I think, 10 minutes.
20 minutes. Okay.
Sir, it was very nice to hear you people again after Nasi TMC program, and I hope that in future we will have opportunity to call you people on campus, and we will have some offline programs. One thing, Dani sir.
Yes.
Actually, our Vice Chancellor has told me that can we plan a certificate course on this Vedic mathematics, or we can say on ancient Indian mathematics.
No, what you are saying? There's some certificate course in mathematics in this
Vedic mathematics. Can we plan some course like this? Is it possible?
Whether we can plan such a course?
Yes.
Should be possible. I mean, Professor Sriram has been involved in various things at that point.
So I have already conveyed my message to Professor Karthik.
Right, we can discuss that. Yeah.
So if you three people can discuss and can provide us a curriculum for that one, it will be very nice, and we will introduce you.
Yeah. Can be done.
Yeah. So I will also talk to you personally, and then we will discuss.
Okay.
Okay, sir. Thank you. So now we will have 10-minute break. Or we can start, Professor Sriram sir. Your mic is mute.
Professor Sriram, you need to.
Yeah. Can you hear me properly?
Yes, now. So I am just saying, can we take a 10-minute break, or you can start?
Okay. No. I think after 5 minutes, shall I start?
Yes, that will be okay.
I also want to have some tea.
Yes. So we can take 10 minutes.
10 minutes and this. Yeah. Okay.
Okay, fine.
Thank
So
you. Yeah.
participants are requested to be connected. We will start at 3:50 sharp.
Yeah.
Okay, okay.
Bala. T.
Priyank, your mic is on. You can mute there.